think the single biggest item that we haven't yet really addressed in terms of the performance of systems is how we're going to deal with problems with big data. People talk about, well, we can use machines for quantum AI, or maybe we can solve large graph problems using these systems or something like that. That remains the single biggest Achilles heel of the systems that are being designed and implemented today. So you can do a system that uses a small number of qubits but has a very complex algorithm, what we call a branching factor, that grows very quickly. So sort of a canonical example would be something like chess or shogi or Go, one of those board game problems where the amount of state you have to represent something is not very large, but there are lots of possible next moves, and so the total possible number of games grows very quickly. It doesn't take a lot of data, but the computation itself actually grows extremely quickly in terms of the total complexity. Now, as it happens, there are pretty good heuristics for solving those problems, and they have a certain structure. So those problems themselves might not be the ones that get implemented as some of the first really commercial applications for quantum computers. But that's kind of the way you want to think today, is what kind of problem has a small state representation but a really complex computational space as it grows. So that's great, but it's going to ultimately limit what we can really do with the systems. And instead, what we would like to do eventually is we would like to be able to work with very large data sets, a large graph structure, or a lot of images if you want to do image recognition, or a lot of language databases if you want to do automatic translation, or whatever it is you want to do. A lot of the most important problems in the world today really require a lot of data. And at the moment, we don't have really good ideas for how you can bring those data into a quantum computer.